welcome, so we can see you.
Whatever you want, Gilberto. And please, doing a brief introduction of yourself.
Yes.
Ok, so, Candida, puoi spengere la telecamera te?
Can you see my screen?
Yeah. I see your screen, I see your face.
Yeah. Well, thank you for inviting me to Meetup Deep Learning Italia. I'm very glad to be here. So, well, I will introduce myself. First of all, I want to talk about hyperparameter optimization with an algorithm called Hyperband. This is actually a novel bandit-based approach to hyperparameter optimization. So this is myself. My name is Gilberto Batres-Estrada, Senior Data Scientist at Trail Technologies in Stockholm, Sweden. I am also a staff member of the Artificial Intelligence Finance Institute, where I conduct some research in deep learning applied to financial time series, prediction of stock returns, and I also conduct teaching of both machine learning and deep learning. I'm also a co-author in one chapter in the book of Big Data and Machine Learning in Quantitative Investment. We wrote the last chapter titled Prediction of Stock Returns with Long Short-Term Memory Networks. I'm a physicist and applied mathematician and came into contact with deep learning when I was doing my master thesis in math. So the goal for today's talk is the following 3 points. Yeah. So I'm doing research in deep learning, especially in long short-term memory networks. I don't have any results yet to show you. So when Matteo asked me to be part of this meetup, I came to think about this hyperparameter optimization method. Actually, I came into contact with this method in the fall of last year, and I haven't experimented with it so much. But it is something that I have started to use during this spring. And I found it like a very, very fast way of doing hyperparameter optimization of neural networks. So I hope that you also find it like a good method for doing hyperparameter search. And hopefully this method is going to help you to do iterations faster and to come up with new architectures of your neural networks. So this talk is actually based on a paper. This paper is called Hyperband, a novel bandit-based approach to hyperparameter optimization. And it was published by Lisha Lee and other authors already in 2018. And they compared this method with, for instance, random search, which is actually a standard method for searching for hyperparameters, but they also compare it to Bayesian methods for doing hyperparameter search. So I'm going to talk about a brief introduction about random search. And I suppose that most of you are already familiar with this because this was like, a very standard way of finding the right hyperparameters for your neural network. As you can see here, we see that they are doing a comparison between grid search on the left here with the random search on the right. And what we can see here is a two-dimensional hyperparameter space. So in the y direction, you can see that the hyperparameters don't change that much. But in the x-axis, as you can see, the hyperparameter might change a lot. And if you are training a neural network, you know that you cannot do as much training as you wish because it costs a lot. You need maybe a cluster of GPUs or whatever. So one thing that you do is that you take only a sample of the hyperparameters that you believe are the right ones. And this image, what it wants to show is that if you are doing random search, you have a bigger chance of exploring the dimension where the hyperparameter changes the most. In this case, as you can see in the right figure, you would have a bigger chance of exploring more values for the hyperparameter. And that's because you do uniform sampling of your hyperparameters. And what is nice with random search is that when you find a configuration that is promising, you have the opportunity to narrow your search in more rounds of your training loop, so to speak. So to be honest with you, I work most of the time with random search. So Bayesian optimization is not my specialty, but they make comparisons with Bayesian optimization because these methods have become standard today. So with Bayesian optimization, what you want to do is that you want to model the conditional probability in this case. This conditional probability would be a probability over some evaluation metric. In this case, it might be the test error, conditional on a set of parameters that you want to test. So the first method that they try in these experiments is called sequential model-based algorithm configuration, or SMAC. Maybe many of you already know about this Bayesian method for hyperparameter search. I haven't used it myself, but what happens here is that you use a random forest to model this conditional probability to get this Gaussian distribution. If you are interested to read about the theory, I have here the author of these methods. The other method that they do comparisons to is called tree structure parse estimator, or TPE for short. It's considered a non-standard Bayesian optimization model. And this was published by Batres-Estrada already 2011. So, and the last one that they try out is called the Spearmint Method. And then here instead you use a Gaussian process to model this conditional probability. And this is the name of the author for this method, I suppose. Yeah. So Hyperband. So Hyperband is an iterative adaptive method for doing hyperparameter search. As you can see here, you see a two-dimensional hyperparameter space showing how Hyperband is doing. So these numbers signify the first iteration and when the best configuration is found. Here, the best configuration is colored in red. And on the right, you can see the evaluation of each of these configurations. And to be honest with you, there was no labels here to see which laws correspond to which configuration, but my guess it will be like they more or less have the same colors as you have in the left, right? So it would be like that. So Hyperband, it's composed of many different functions or subroutines, as you can call it. One subroutine that is used in Hyperband, it's called successive halving. And this method was already published, successive halving, in 2005. And as the name suggests, what happens here is that you do an iteration searching for the best hyperparameters. And what you do is for each iteration, you evaluate the error metrics, and then you throw away half of the metrics that are the worst, so to speak. Actually, there is a parameter that can regulate how much proportion of the configurations you want to throw away. So it doesn't have to be the half. You can change that with a hyperparameter, with a parameter in the function. And you continue with this till you find the best configuration. One issue with this original successive halving, it was that you have to make a trade-off between how many configurations you want to use against a budget. So that's an issue. And well, the thing is that Hyperband is not a silver bullet, so it's not going to solve all your problems either, but it's a little bit better than successive halving. So you have always trade-offs, but maybe the trade-offs that you gave away with successive halving when you go to Hyperband are easier to cope with, I would say. So what is required for you to use Hyperband is the following. Is to implement three functions. The first one, as you can see by the name, is to get a hyperparameter configuration as an input to the algorithm. And the second function is that when you are doing an iteration for training, you get a set of configurations. And in the third step, you are going to rank these configurations and just keep the ones that are the best in that run. So the algorithm looks like this. There are two hyperparameters. The first one, R, stands for resource, and then you have eta. Eta is something that you can see here is used for regulating the proportion of hyperparameters that you want to keep for the next iteration. So there are two for loops here. So the inner loop, it's calling this successive halving, as you can see here in the comments. So in this first loop, first you get the hyperparameters or the hyperparameter configuration. You do the for loop here, do the training, and get the best, or you get the result of the configurations of hyperparameter that you have found, and then you rank them, and then you loop again. But that's easier said than done. So as you can see here, this is an example of what it's called terminal validation losses. So when you are doing training, each validation loss is going to be have some kind of envelope function that is called here. It might be some confidence interval or something like that. A priori, you don't know the distribution of the terminal losses. So the resource, choosing the resource is one of the things that you have to do. They have some default values that you can use, mentioned in the paper. For instance, if we go back, they tend to use, well, it actually depends on what kind of resources you want to use as a resource. Actually, to be honest, you can use anything you want. You can use, for instance, the number of iterations as a resource. You can use the time of training. Somehow you can put it there. Maybe if you know that each iteration is going to take 10 minutes, then that's somehow how you can regulate the training time. You can also do data subsampling, for instance. And so these two parameters in the function are going to create this budget parameter here. So you have a budget. So you have like trade-off that we had in Hyperband, the number of configurations against the budget. But the budget is regulated here by the parameter R. So as you can see, the validation losses, they can like be very near together. So if you are using here in the x-axis, for instance, the number of epochs as a resource, you can see here that we are like trying to separate these validation losses when you have done training for 200 epochs, for instance. So that makes it difficult because you don't know this in advance. What you should do is that if you know you have some domain knowledge about the problem, you can use that knowledge to make the training easier. If you know that the learning rate is going to be around a certain value, you use that value, and you are free to choose that you don't want to search for the learning rate. So you can choose which hyperparameters you want to search. This is an example that they run. And let me remind you, I forgot something. One iteration in the inner loop is called for a bracket in the terminology of the paper. So they refer to this as a bracket, each iteration. So they did a test for the network. And as you can see, you start from bracket number 4 down to bracket number 0. And here the parameters of the function, how they change. So at the beginning, what the algorithm does is that it divides resources equally to all configurations of your hyperparameters, but trains for a few iterations. And then that's something that you have to change what you want. If you want to make the first search a certain amount of iterations, you have to choose that, and you just compute that according to the formulas here. So then at the end, the winning hyperparameter configuration is going to get like the most iterations, right, that you train on those. What you can see here is the validation or the test error. What you see in red here is the test error for random search. So as you can see, and this S0 to S4 represent each of this bracket or the inner loops in the algorithm. So each individual bracket is plotted. And as you can see, the bracket number 3 is the most optimal. You don't know that when you are running your Hyperband search. So that's at the end that you are going to get the best configuration from your algorithm. But it's something like a black box, but they chose to plot all of the different brackets. And as you can see, the test error reaches a very low value. Well, the worst one was the bracket number 1 here, almost at the end. But at the same time, you can see that the test error got very low with a few seconds of training or less than random search. So when you do the training, you specify like Hypercube of your hyperparameters. So this is the Hypercube for the hyperparameters of the network in this experiment. And they conducted many more experiments. I will show only one more. In this case, they trained a convolutional neural network published by Snowick here in 2012. They don't say what type of architecture they used. They had a link. I tried to click on it, but it didn't work. So please feel free to search for this paper and see the architecture. So what you see in parentheses here, first is the CFAR 10 dataset. composed of 40,000 training examples, 10,000 validation examples, and 10,000 test examples. Then you have the rotated MNIST with background images. And this is the training part, validation, and test. And then you have the Street View house numbers with 600,000 training examples, 6,000 validation examples, and 26,000 test examples. And you can see the results here. So they are comparing these algorithms that I mentioned before. When it says early in parentheses, it means that they are also combining this SMAC algorithm with early stopping. So as you can see, Hyperband achieves a very low test accuracy already after very few rounds or number of resources used in this case. In this case, you see the other data set, the rotated MNIST. Also, you can see that Hyperband is behaving very well. And what I want to show you with this is that it's not that you have to train for a very high number of resources, but what is showing here is that you can achieve good enough results already after less resources than the other methods, you know. And in the last example here, well, here actually this SMAC with early stopping was much better actually here at the end. So I mean, even though you can have better accuracy, you are achieving good enough already after 20 number of resources used. If I recall correctly, in this case, they were using the number of epochs as a way of computing the resources. So when Matteo asked me to be part of this meetup, I wanted to do the implementations myself, but then I thought maybe I will search the internet, and I found Keras tuner. So Keras offers already hyperparameter search, and you can do both random search, Hyperband search, and also you can do Bayesian search. I will show you how to use it. I run a long short-term memory network. I use a data set from Google. Here is the link. This link goes to a tutorial about long short-term memory networks. So actually I have used most of their code, which I have implemented as functions here. In other files, I call these functions in my notebook. First, the problem is to predict the temperature. You see the data set here. So you want to predict temperature. And we want to predict one time ahead of time. And you have all these features for you to use as input for the model. First, this is some plotting. First, we have how does it look with the historic data and what you want to predict in this case. Then we have a baseline, which actually is only the average of the time series. So you can see here the model prediction just taking the average to the real label. Then we use some features to do the prediction. Yeah, you see how the time series looks like. You do your classical split of, I did it before, right? Train and test sets. And then you do the normalization as usual. In the first case, I'm just training a regular long short-term memory network. which is coded here. Here is the single model. It's just a classical non-short-term memory network with only one layer, 32 neurons, and using the mean average error as the loss, using RMS prop. So it's nothing fancy. Just to show the point. So we run this for 14 seconds. And the predictions of the model are these ones on the validation set, so quite okay. And the network was trained also only for 2 epochs, so that's not that much. Then only 2 points, so it's not that informative. So, so hyperparameter search in Keras. Well, I did a class called time series LSTM with one output in this case. There is the possibility to control how many outputs you want to have, meaning how many time steps ahead you want to predict. You have the hyperband here that you call from the Keras tuner, and you pass this model, which I have coded here, the time series LSTM that has to be subclass from the hyper model. And it's nothing fancy here either. The only thing that is required of you is to build or construct a function called build. And you have to have this object from the Keras tuner. This is the hyper. Well, yeah, it belongs to the Keras tuner anyway. So you have to pass it here. And the optimization, well, it's very easy. You can both you can sample the number of layers if you want to. I didn't do that, but there are many examples in their homepage. In this case, we are sampling the number of units. And as I told you, this is a hypercube. So the mean value is 10 neurons. The maximum value is 200 neurons for a step of 32. So you are going to increase for each iteration how many neurons you are going to add. Here the learning rates, you can change them if you want. It's not necessary, and so on. So it's not that difficult. Before I forget, all this code I have put in my repository, which is going to be part of this presentation. So I have the link at the end of the presentation. So you have access to all this code, and you can also make your own experiments. You can combine it with TensorBoard if you like to. So actually, I trained this only for 2 epochs, which resulted in a training of 7 minutes and 29 seconds. I did a lot of experiments during the weekend. This is the predictions of the model. Actually, I don't see that they are much better. Maybe they are than the regular neural network. And then at the end here, you use also the random search. I compare it to it. And it's very funny because I told you that the authors say that you can achieve at least 1 order of magnitude faster results with Hyperband compared to Bayesian optimization. In this case, when I was trying random search in Hyperband, they achieved the same time because it was very few rounds of training. But in earlier experiments that I did, when I used, say, 10 epochs, I saw a very huge difference. Random search maybe took 20 minutes, and Hyperband maybe took around 7 minutes or something like that. So, but my problem is that I ran this experiment before the meetup, and I didn't have the time to to run a bigger experiment. So yeah, so these are the results. And this is a good way to do hyperparameter search. So this is the Keras tuner. You can code it yourself if you want the Hyperband. It doesn't seem to be that hard to do it yourself. So, but let me say something before I finish. And one thing is that you can combine Hyperband with other methods. So for instance, if you know that about cyclical learning rate, which was published by Leslie Smith, he suggests that you can make well, you can implement your learning rate as a cyclical learning rate, which means that it's going to go up and down during training. And he shows that it gives faster results or better results than regular, than other learning rate schedules. I think that Fast AI, which is based on PyTorch, they implement actually this already. So it's a default that you can both find the values for cyclical learning rate and just run it right away with Fast AI. But if you want to implement this yourself, say in TensorFlow or Keras, you have to do like something like this. Local stands for a local variable. I suppose this is in Torch. And you define your first X, and then X is going to be used here in the learning rate. So it's not that hard to find this, but the problem is maybe to find the maximum learning rate, which means that you increment the learning rate till you get a very bad result, then you stop, and that's the max learning rate that you are going to put here. If you want to do it in Keras, you write a scheduler. You write, instead of having these lines of code, maybe you have something similar to this cyclical learning rate, and then you can have it as a callback in Keras. That's one way to have it. And maybe combine, I haven't tested myself. This is something that I'm planning to do, but it would be nice to test both Hyperband and this cyclical learning rate. So here you see some contacts for me. My repository here is the link, and these are some of the papers that I have talked about this evening. So I think that's all for me, folks.
Thank you, Gilberto.
Thank you so much.
Yeah, it was very academic presentation.
Sorry.
like professor. No, it's very nice, very nice. So there are any question in this particular topics? I know it's maybe a bit for advanced people and not for junior, but any question?
We have Alessandro that are saying bravissimo. So
thank you.
Did you try this kind of optimization, some kind of financial problem?
I am trying to do that actually. That's why I was looking for new optimization methods, because I found that random search, it can be hard to find good hyperparameters. So actually I just started this spring to use it. I don't have any results yet, but I'm using it now. Yeah.
Okay. Do you think it's much computational? It's much hard for computational stuff doing this kind of optimization? Or what is your suggestion if you want to try a new way to optimize your parameter? Maybe try random search, grid search, and after try this. Okay, Matteo, you have to try this before because it's such a beautiful thing, and you can find the perfect balancing for your.
I would say, yeah. Well, it's not a silver bullet, so that's why I suggest to combine it with this cyclical learning rate. So that's why it's not a silver bullet, and as I show you in some other experiments, Bayesian methods are also better. But one issue with Bayesian methods, as I have understood, is that it is more complicated to do the training than it is with Hyperband. It takes more time, almost one order of magnitude with Bayesian optimization. So only that you can get good enough results faster, it's a good thing, I would say. So for me, it's going to be like my method of choice for doing hyperparameter search. That's for sure, because random search, which I have used, it can be frustrating sometimes because it means that you have to have some idea of the hyperparameter space, right? So that's sometimes you are lucky. You can find a very good hyperparameters with random search, and then maybe narrow your search when you feel that, okay, these are good enough. Maybe I will try more runs of random search. But at the same time, I think Hyperband, it's as I have seen it here, a little bit faster. And yeah, I mean, it cannot be much more worse than random search and Bayesian optimization. So yeah, I would say definitely try it out, and try it now that Keras tuner exists. It makes the work easier. So
okay. So you have to try a different way, and maybe this can be better than one, but depending of the use cases, the data, and which kind of problem you try to solve. Because maybe if you want to, from my experience, if you want to, when you're using optimization, for example, in NLP method, sometimes it's much faster than when you try to face up a time series prediction method, for example.
Yes,
depending of the data and what kind of data you have, and how much do you have. In financial problem, you have million of data if you want.
Yeah, that's true. But one thing with Hyperband is that you can do feature subsampling also, right? So because as Candida mentioned in her talk, I think I understood a little bit of Italian. She was talking about the budget in computation. I hope it's right. And that's one problem that we are facing today, because you are moving your computations to the cloud, and that's not for free, right? So I think that there are many other parameters that you can sample or use as a resource allocation for your hyperparameter search, I would say. So I think it's not a silver bullet, but I think it's a very, very, very good method.
Okay, do you think this kind of method could be helpful if your data set is unbalancing, or if your data set have different distribution and variance? Because this is the big problem of when you have a lot of data, but there are no balancing, or they are from different distributions. So you have to divide by meaning, try to standardize all the data. What do you think about that?
So your question is if the data distribution has some performance, if it's going to hard performance in Hyper. That's the question. Well, I think that especially when you are working with financial time series, the distribution change with time, right? So I believe that depending on how you do your training, if you have the opportunity to retrain your network, this is going to be a very good help, because if you have to do many iterations, or if you have to train your model regularly, it's going to take less time to retrain your model, right?
You mean a full retraining, or just
a full retraining? Yeah.
Retraining. Okay.
And especially if you are doing computer vision, just training for a few epochs, and I don't know if you would need to do a full retraining. Maybe you have to. And as you have seen, I was reading an article today about how COVID has changed the way people behave. So it means that many of the AI models deployed are suffering because the data distribution has changed, right? So, in that case, you have to retrain the model. And the question is, do I have to retrain it with my old method, Bayesian optimization, which I'm not a specialist on Bayesian optimization. So, but according to what I have read so far, is that Hyperband is faster. So only that gives you an advantage for doing the retraining.
Could be a choice. Could be a choice.
Yeah, could be a choice. Yeah.
Okay. It's time for Mehdi. So thank you, Gilberto, for your time, for your speech, for your presentation, and